So we're going to shift gears a little bit today. We've been spending some time thinking about how to make programs run faster. And the last couple lectures were all about pipelining the beta, where we're taking basically a single program. Here's a single program. And we're interested in running it as quickly as possible. And of course, in the end, it's not the assembly code that's important. What's actually important in the execution of the program is the list of instructions that gets executed, in the course of running the program. So in the case of a loop, the actual back and forth, going back to the top of the loop and coming down again is sort of important to our ability to execute it very expeditiously. And in particular, the fact that we're going through this loop many times means, for instance, in caches, that once we get these instructions into the cache, they'll be there the next time we go look for them, and assuming the cache has the right architecture. So that means that these sort of repeated executions of particular instructions is one key for us to be able to execute programs much more quickly, because for example, our cache architectures actually work. So if I actually want to think about what it takes to execute this program, I'm sort of interested in the total path length, the total number of instructions that get executed. Okay, and we've been working hard on trying to execute each instruction as quickly as possible. So we introduced pipelining to sort of get the clock rate of the processor up. And so if you think of the total time it takes to run a program as the total number of instructions times the clocks per instruction, that's 1 for us. So if we take the total number of instructions and we're doing one instruction per one clock per instruction, and then we have how many clocks per second, and pipelining allowed us to get more and more clocks per second. That was the goal of doing our pipelining. And so today what we're going to try to do is to see if we can improve on the number of clocks per instruction. We'd like to make it, if we could, less than 1. Our machine does 1 clock for each instruction, 1 instruction per clock. That's either way, that way. But the question is, can we do more than 1 instruction in a clock cycle? Can we do 2 at a time? And so we're spending a little bit of time thinking about different ways of gluing together our processor building blocks today to figure out if we can have the effect of getting more than 1 instruction per clock cycle. And you see that the machines that you have in front of you will actually be a collection of these techniques, a hybrid, and I'll point that out as we go along. So there's 2 opportunities here. One is instruction level parallelism. So that's you have a single program that you're trying to run, and what we're going to try to do is to execute more than 1 instruction at a time. And as we'll see in the next slide, sometimes that's pretty easy to do, and sometimes you're sort of saying, gosh, those, I can't do them both because I need the first one to finish before I can do the second one. And so it's sort of struggling with those sorts of constraints that make instruction level parallelism hard. And a lot of transistors inside your Intel chip are devoted to finding things that can happen in parallel, and then having a couple of different functional units which can operate on 2 different instructions at the same time if the semantics of the program allows that. Maybe more realistically, and this is sort of the direction things are headed in, is thread level parallelism. So that means we actually have 2 different independent things, and we're just going to execute them both at the same time. And the net effect is the machine is busily executing 2 instructions or 4 instructions at once, depends how many cores you have. Some of you have 2-core machines, some of you have 4-core machines. And the reason everybody's happy to run in parallel is there's no what's happening in program A has no effect on what's happening in program B. So in fact, you can execute 1 instruction from each program without worrying about, do I need to wait for the first instruction to finish before I can do the second? The answer is no, they're in different programs. So thread level parallelism is sort of, it's easy from a hardware point of view, and maybe even easy from a software point of view.